Hello and welcome to another exciting video on applied electronics tutorials, Ayoki. And today, we are going to focus on the transistors. Yes, that's what we are going to focus on for today. Specifically, the BJT, That is the bipolar junction transistor. Bipolar junction transistors. That's what we are going to focus on. And under the transistors, what are you going to talk about? We are going to talk about the mode of operation. The mode of operation. Of the BJT. Then we'll also talk about the circuit analysis. Circuit analysis of the BJT. Then you finalize our section or this video with the collector characteristic. Basically, that's what they are going to do. You get it. But before we dive deep into this, please, I encourage you to watch the previous video, very well, and understand the concepts very well if you've not watched it, Then also, you subscribe to the channel. That is, if you've not yet subscribed, then you also join the Telegram page, Join the Telegram page as well, where you get the opportunity to ask any question that you want to ask, And you also get us solving your complicated questions. Yes. So we are going to talk about the mode of operation, So let's move to the mode of operation of BJT. Yes. Very good. So with the mode of operation, how do you see? First of all, what's a transistor, If someone should ask you what a transistor is. A transistor is just is a three-terminal semiconductor device. Which can act like a switch or an amplifier. So this is the definition of a transistor. So a transistor is having a three terminals, It's a three-terminal semiconductor device, Which can act like a switch. So these are the key ways that should come in any definition of a transistor. So let me typically draw how a transistor looks like in a real world, It's something like this. We have a P region here. Then we have, let's say, let me use a different thing, to draw those sides, And we also have a P region, and we have another N region, something like this. Or this can be an N region, then we have P region, and we have the N region, Or it can also look like this, the same structure. Let me use this one, I have this one here, and the N region comes in the middle, We also have another P region, something like P and P. So all of them has a lead, like a terminal at the end. So the N is having a terminal at the end. The P is having a terminal at the end over here, which is basically the base, And another N is also having terminal. Any of the N can be what? either emitter or collector, depending on the doping. Okay, I'll talk about it later on. But let's assume this is the collector of the parts, and this is the emitter, right? Emitter, and this is the base. Always the one at the middle can be considered as the base. The same way, this can be the collector, right? That's the collector lead, and we have the emitter lead, emitter, and this side can be considered as what? As the base. Okay. So, what's the difference between the base, the collector, and the emitter in terms of doping, right? In terms of doping, what is the difference? The base is lightly doped. You should take note of it. The base is lightly doped, right? So it's lightly doped. That is lightly doped, right? With the P or the N. That is when it comes to the PMP. But if it comes to the MPN, it's lightly doped with what? With both. Whilst the collector, right? The collector is moderately, right? It's moderately doped. Moderate. Right? Moderately doped. There's E here. Sorry. So the collector is moderately doped. Right? Then the emitter, which is in terms of doping, right? The emitter is heavily doped. Let me use the. So it's that side is right. It's H. Sorry. So the emitter is what is heavily, right? Right, it's heavily doped with, how do you call it? So it's heavily doped with the semiconductor material. Okay, so you should take note of all the parts. This is the N region, right? Then this is another N region, right? N region. This is the P region. Right. And this junction can be termed as this junction, right, can be termed as the base collector junction, right? That is the base collector or collector base junction, any of them. So this is the base collector junction. I'm talking about it later on, so we take note of it. And this side can be considered as the base emitter junction. That is this side, this junction, or this region, right? It's termed as the base emitter junction, and this is the base collector junction. You should always take note of it, right? The same applies to the PMP transistor. This is the PMP transistor, right? And this side is also what? The MPN transistor. This one is also what? The MPN transistor. Whatever happens in the PMP transistor, it also happens in the PMP. That whatever happens in the MPN is also happening in what? In the PMP transistor. You should take note. With the collector side of the transistor, that side too is moderately doped. The base is lightly doped, right? And the, how do you call it? The emitter is heavily doped. You should take note of it. It can be an objective question. Which of the following is heavily doped, or which of the following regions or part of a BJT is heavily doped? So you should take note of it. But our main focus is going to be on the MPN transistor. So let me sketch it. Let me sketch it somewhere here. Right. So anything that we talk about the MPN transistor, it applies to what? To the PMP transistor. So we have N region here, which is lightly doped, and P region, we have another N region. You get it. Whilst this place can be considered as a base, this can be considered as what? As the collector, right? And this side is considered as the emitter. Okay. So, you see, in our previous diagram that I showed, we said this is moderately doped, right? So it's moderately doped. Do you get it? Sorry, let me write it all. So moderately doped, and this is lightly doped. Okay. This is heavily doped region. Do you get it? So in that case, if I should sketch this diagram again, showing the electrons. Okay, so let me sketch this one very well, showing all the electrons in the regions. So since the emitter is heavily doped, the emitter will be having more electrons compared to what? Compared to the collector. So let's say if this one is having about 30 electrons, then the collector will be having, how do you call it? The collector will be having, let's say, few electrons in them, because it's like moderately doped. You get it? So the electrons will not be many compared to what? That of the emitter. Then this is the positive side, which is having some have more positive there, the P region. Okay. So how do we connect our batteries? So we connect the positive terminal of the battery here, and we have the negative terminal at this end. Okay. Then the base is always fed with what? The positive terminal. Right. So we have the base here, we have the collector here, and we have the emitter here. With this type of configuration, the collector base junction is always seen to be what? To be reverse bias. Right. Right. And let me spell the bias well. So this side is always seen as what? As reverse bias. Then this junction, right, which is the base emitter junction. It is the base collector junction. This side is seen as what? As forward bias. Right. So how do we see it? See, you see, in our diode, we said that to create a forward bias, let me draw the diode here, right? If I have P region here and N region here, we said the P region is connected to what? To the positive, and the N region is connected to the negative. That's for forward bias of a diode. If you've not watched my diode video, please try as much as possible to watch it, so that you understand the meaning of forward bias and reverse bias. So why do I say that? Why do I say that this junction is forward bias? Because see, the negative is connected to what? To the negative of the battery, right? And the positive is connected to what? Positive. Do you get it? So the positive is connected to positive, and the negative is connected to what? To the negative. So in that case, it makes this junction what? A forward bias junction, right? And what about the BC junction? The negative is connected to positive, right? And let's say this side is connected to the negative. In terms of this, the positive is connected to the negative, right? If we should take just the base and the collector, so it makes this side more like what? A reverse bias, since the negative is connected to the positive. So it makes it look like a reverse bias. So how does the operation take place? Because this junction, the BE, right, is forward bias. As soon as I power this device, the electrons begin to what? Flow to the region here. begin to flow to the P region. And since the P region is lightly doped, you get it, few of the electrons will be moving to this side, which is the base side. Since it's lightly doped, you have less electrons, right, moving to that side. So the remaining electrons, how will they move, right? They will break the potential barrier of the BC region. Then they will begin to move to the N region of the collector. So as they move to the N region of the collector, this positive attracts them, right? And once it attracts, then it causes current to flow in this direction, right? That is the electron direction. That's the electron current. So the electrons will be flowing in this direction, because not all the electrons that flows to the P region move to the base. Because this is lightly doped, only few of them will be moving to the base. And as they move, more electrons are moving to the base side. So because there are more electrons moving to the base side, part of them, or the remaining ones, will find their way through through the N region of the collector. Then once they move there, then the electrons will begin to move in this direction. Electrons will begin to move in this direction. So once the electrons are moving, then the current, that's the conventional current, will flow north in the opposite direction. So then the currents will begin to flow in the opposite direction. So that is how it operates. It operates because the N region here, the emitter side is heavily doped. You should take note of that. And the base is lightly doped. That is, we have few positive, like few holes, right, at the NP region, that's the base side. And we have moderately doped at the collector side. We have electrons there, but the electrons are not many compared to the emitter side. So once this is a forward bias region, then as soon as I start operation, then the electrons, right, begins to flow towards the base side. Right. So once they flow here, because the P here is attracting the electrons, some of the electrons will be moving to the base side of the terminal. Do you get it? Will be moving to the base side of the terminal, but it's slightly doped, right? And more electrons are moving there. So because some of the electrons also want to have their way out of the base region of the transistor, they are forced to move to the collector side. Once they get to the collector side, then the positive terminal here attracts them. The positive terminal attracts them, and they begin to flow. Are you okay? So at default, when we've not started the operation, then this junction will not allow the current to flow. But as soon as we allow the operation, this potential barrier, which is basically more like the 0.7 volts, right, will be broken. Then once it's broken, right, then it begins to cause electron to move in the N region, and the current flows. So that's how it operates. So you should take note of it. In the schematic diagram, if I should show it, it's more like I have it to be something like this, right? I'm drawing the NPN transistor. So with the NPN transistor, the arrow is always pointed down. So this is an NPN transistor. Assuming it was a PNP transistor, right? The arrow will be pointing what? Will be pointing upward. To be pointing upward. So you should take note. If it's a PNP transistor, the arrow will be pointing upwards. Right? The arrow at the emitter junction will be pointing upward. So that's the only difference. With PNP, the arrow is pointing upward, and with NPN, right? The arrow is pointing downwards. But we are going to focus on what? NPN transistor. So let's put this one aside for now. Okay, so with this terminal is considered to be what? The collector. And this terminal is considered to be the emitter, right? That is the E. And we have the collector here, which is C. And we have the base here. So what happens? The base is powered with a positive terminal. The emitter is negative. Then we have a positive battery terminal connected to the base. So what happens here? This junction, right, is termed as the base emitter junction. This side, there's a junction here which can be considered as the base emitter junction. And there's a junction here which is considered as what? As the base collector junction. So at the base collector junction, this side is a reverse biased. Right. And this side is forward bias. You get it? So once it begins to operate, then the electrons flows to this end. They flows, and as they flows, some of the electrons flows to the base, right? And the ones that are remaining, right, flows towards to the collector side. So the electrons will be moving this way. So once the electrons are moving, then the conventional currents will also be flowing in the opposite direction. At this point, I assume that anyone watching my video have an overview of the conventional current. You get it? So you should be able to understand what conventional current is. You get it? Yes. So this is how it operates. That's the mode of operation. Before we dive into the circuit analysis, right, I want to make a schematic diagram and expose you to how the BJT works. So in order to make like a schematic diagram for the BJT, the NPN transistor, this is an NPN transistor, right? We need the NPN transistor, right? We need a base resistor, which is normally referred to as the RB, right? And this is just a switch to control the current that is flowing through the base of the BJT, right? And we need a voltage source for the base. Then we need the main source, right? We need the main source. This is the main source. Then we also need, how do you call it, a collector resistance. Okay. Then all these ones are connected to ground. So we need, like, let's say, a ground circuit, right, over here in order to make a complete circuit. So let's do the connection. So with this, right, the base is connected in this way, like how I'm doing it, right? The voltages have already been set, so you don't need to set the values again. Then we need to connect the emitter to also the ground. Then the collector side is connected to what? To the collector resistance. Then we have, how do you call it, the source voltage for the control, right? Then we need, how do you call it, to join the negative side to the emitter. We made it clear that the negative is connected to what? The emitter, and the positive is connected to the collector. Okay, so let's look at the current view. What happens? Once I feed the base, right, current begins to flow. Initially, I told you that this junction is termed as what? The base emitter junction, and it's basically forward bias. And this side is the base collector junction, and is reverse bias. So at this state, the current is not going to flow, right? Because electron is not flowing. Electron always flows this way, flows upwards, right? So once electrons are flowing, then conventional current will also flow in the opposite direction. So the current flow here is more like conventional current flow, right? The direction that you'll be seeing, the current flow that you'll be seeing here is the conventional current flow, which will be moving upward this way. It's moving downwards through the, how do you call it, the BJT. But electrons are flowing, let's say, upwards. That is the electron flow. So let's click on the play button and see what happens. Right. So at this point, you see it's not operating because the base has not been fed with any current. Okay. So once the base is fed, then it closes this side for current to flow. Right. So let's close the switch and see what happens. So you see, conventional current is flowing, and conventional current is flowing downwards. So why was conventional current flowing? Conventional current is flowing this way because the electrons are flowing in the opposite direction. Please take note of it. The electrons are flowing upward. So it is causing the conventional current to flow. Right? So once I open the switch, then it stops flowing, current stops flowing. So once I close the switch, then current begins to flow. So in this case, the transistor here is acting like a switch. The transistor is acting like a switch. So you should take note of it. Right. So that is how it operates. So once I close the base, then the base closes the reverse bias here and the electrons begin to flow. Right. So once the electrons are flowing, then current is flowing in the opposite direction. So at this point, you see the direction of what? Conventional current. So please take note of it very well, and it's very, very important. Right. So with this one, the transistor is acting like a switch. So once I open it, then the current will not flow. Right. Current will not flow. But once I close it, right, then the current begin to flow. Okay, in order to make it clearer to you, right, let me introduce, how do you call it? Let me introduce a light bulb. Right. Okay, let me close this one and introduce an LED. Let me see whether we can get an LED over here. That's light emitting diode. Right, light emitting diode. Then let me pick an LED and place it into it. So let me close this. And with LED, let me place it at this end. So with LED, the positive is connected to what? To the positive. And the negative is connected to what? To the negative. So let me rotate it this way. Then the positive is connected to what? To the positive terminal. The negative is connected to the positive. Anode side is connected to the positive. And negative is connected to the negative. Let's see what happens. Will it turn on? Let me see. You see, very good. So I want to control this light here, right? Basically, this is more like a separate circuit. This side is a separate circuit. That is the control circuit, right? The base side is the control circuit. I'm controlling the current that is flowing to the base. And once I control the current there, the BJT can act like an open or what? A closed switch. So once it acts like an open switch, then the current will stop flowing through what? Through the collector and the base, right? But once I close the base, then the current will begin to flow, and any load that is connected to the circuitry side will begin to operate. So this is how a bipolar transistor works. Okay. So let's move back onto our board. Right. Let me draw the schematic diagram again over here. So this is how we have. This is what we have. We have our point here. We are going to move deep into it. At this point, we are going to talk about the circuit analysis, right? Circuit analysis of BJT, right? So with this, we have the PNP transistor, NPN transistor. Sorry, that's what we are focusing on, right? So this is how it looks like. Then I have the RB here, RB, which is the base resistance, right? Then I have the base voltage, positive, negative, positive, and it's connected to what? To the ground. Let me connect it to ground, right? Then I also have the emitter, which is connected to what? To ground, right? Then I have my collector. So we have the collector resistance. Then we also have the battery to the collector side, which is positive, negative, positive, negative, positive, negative, and it's connected to what? To ground. So in the books, this is what you see. This is the VCC. Like, do you get it? This is the same as joining them together. What I've drawn here is the same as joining them together. It means that they are all sharing the common point, which is the ground. So I can draw it this way, where I have it moving to this end, and this one also moving to the other end, right? I can join all of them like this, and they are connected towards to ground. Do you get it? So knowing the terminals are very, very, very important. This is RC, VCC, right? And this is the emitter side, which is the E. And we have the collector side, which is the C. And we have the base side, which is the B. Right? So how are they arranged? Because up there, right, is reverse bias. So this side is more like reverse bias. Let me clean it right here. So this side is reverse bias. Let me make it RB, reverse bias. And this is forward bias, right? So because here is forward bias, the terminals are more like positive and hot and negative, right? This side is positive and negative, and this side is negative and positive, right? That's the base collector side. We have negative here, we have positive here, and the base emitter side, we have positive and we have negative. Then this side, right, since the current is flowing this way, we have positive here and we have negative here. We should take note of how the polarities are arranged on the transistor. Between the collector and the emitter, positive is located at the collector side and negative is located at the emitter side, right? And with the, how do you call it, between the base and the emitter, we have positive at the base side and we have negative at the emitter side, right? And between the base and hot and the collector, we have negative at the base side and we have positive at the collector side. So you should take note of it very well, and it's very, very important, right? So this side, the voltage over here, the voltage at this terminal is termed as VCB, right? The voltage here is termed as VCB. The voltage here is termed as VBE, right? That is the collector base voltage, and this side is the base emitter voltage, and we have VCE, right? The voltage at this terminal is termed as the collector emitter voltage. So you should take note of it. It's very, very important. And how does current flow? The current at the emitter side is called the IC. That's the collector side, sorry. So it's called IC. Let me erase it and use red ink to show the current directions. So we have IC here, right? And the emitter side is also moving downwards, right? Which is called what? IE, right? And the base current is moving this way. We saw it clearly. We are showing the conventional current direction. So we saw that the current was moving to the base side. So it's termed as what? IB. Do you get it? Yes. So from Ohm's law, if this is seen as a node, then what do we have? We are going to have the sum of current entering the node is equal to the sum of current leaving the node. So we can see that IC is what is entering the node, IB is entering the node, and IE is leaving. So we can see that IE is equal to what? IB plus what? IC. Right? That is it. IE is equal to IB plus IC. Okay. But before we move deep into this, I want you to know these two keywords. That is the beta DC, and we also have the alpha DC. Okay, so I'll talk about this one later. That's the current gain, okay, the static current gain. We are going to talk about it later. But let's complete the circuit analysis. Once we are done, I'll talk about the beta DC and the alpha DC. Are you okay? Yes. It's relating to the base current, collector current, and the emitter current. But before I dive into it, let me make all the analysis of this. Are you okay? So at default, since the current is flowing this way, this side is going to be what? Positive and negative. That the current is flowing through it this way. We are going to have positive, negative here, and this side is going to be what? Positive and negative. Okay. And this can be considered as VBB. Right. That is VBB. Right. So what happens if I should write a KVL equation for the base side? If I should write a KVL equation for the base side, what am I going to get? The base side KVL equation. I'll say that VBB, the voltage drop over here, right, or the voltage at this end, and you see this RB is also having a voltage drop, which can be considered as what? As VRB, right? The voltage drop at the base resistor. Okay. So I will say that rising is positive and falling is negative. So VBB minus VRB, right? Then this one too is also a drop, right? So I'll say minus VBE is equal to 0 from KVL, considering this loop. Considering just the loop here, yes, this side. It's a loop, right? So if I should consider it, then I'll say that VBB minus VRB minus VBE is equal to 0. And with this, if I want to find VRB, what do I get? I'll say that VRB, right, is equal to what? It's equal to, I'm going to send VRB to this side of the equation. We get it. So VRB is equal to what? VBB minus what? VBE. Do you get it? Yes. But what is VRB? The voltage drop here. It's the same as VRB is the same as what? It's the same as the resistance minus what? The current. That is Ohm's law. V is equal to IR. So the voltage drop here is the same as multiplying what? The current and the resistance. That's IBRB. So on this note, if I should consider this equation, let me call it equation 1. I will say that IRB multiplied by what? RB, right, is equal to, or let me say IB. That is the IB, not IRB, right? But let me make it IB so that you not be confused. So IB multiplied by what? RB is equal to what? VBB minus VBE, right? So at this point, what do I have? I'm going to get IB is equal to what? VBB minus VBE, all divided by what? all divided by RB, right? And this is a key formula you need to know. If you are asked to find the base current, you will need this in finding the base current. At times, you always need this in finding the base current. Okay, so if we are done with that side, let's also consider the other loop, the main circuit loop, the circuit control. This side, let's consider the loop here. Right, this is also another loop. Right, it's a circuit which is having like a closed loop. Okay, so at this point too, there's a voltage drop here which can be considered as what, as VC, right? That is the voltage drop at the corrector side, or VRC. Let me use that. That'll be better. So the VRC over there. So if you should consider this loop, right, to write a KVL equation, let me write it at this end. The VCC, which is a rise in the voltage, VCC, right, minus VRC, right, minus VCE, minus VCE here. That is it in a closed loop. The voltage here minus the voltage here minus the voltage here, right, going back is equal to what? To 0. Are you okay? Yes. So if you want to find the IC alone, or the current IC, right, we need to make VRC the subject. So in that case, what do I get if I just send the VRC here? Let me go down and write it. I've already obtained the VCC minus what? Minus VRC minus VRC minus VCE equal to 0. So in that case, I'll say that VRC is equal to what? Is equal to, how do you call it? VCC, right? I'm sending VRC to this side of the equation, which will be positive. So we left with VCC minus what? VCE, right? Now what is RC? RC is just equal to what? The IC multiplied by what? RC. In that case, I'll say that the VRC is IC multiplied by what? RC. Or equal to what? VCC minus what? VCE. Right. So what will be RC? I'll obtain RC by what? Dividing both sides by what? IC. No, I'm looking for IC rather. So to find IC, I just divide both sides by what? The RC. So I get VCC minus VCE, all divided by what? The RC. Yes. And this is also another formula for finding what? The collector current. Okay. So this is the base current. If I want to find the base current, after giving the base voltage and knowing the VBE, right, knowing the RB, I'm going to what? Get this formula to find the IB. And the IC, knowing VCC minus VCE, all divided by RC, right? So if I want to find the emitter current, I just use the KCL equation that I showed above. That is the IE, right? IE is equal to what? So the IE was equal to what we located there. That is IB plus what? IC. IB plus IC plus IC. So that is the formula for what? For the base, emitter, and the collector current. All the currents over there. These are the three things that you need in finding the current. Nobody is going to ask you to prove, right? But understanding the proof is going to what? Help you solve a lot of what? Questions without knowing the formula, right? Once you understand how all this thing comes about or how it came about, If you have forgotten the formula at the exam, so it will be easy for you to what? To solve it. Do you get it? Yes. So, but the VBE, it depends on the type of material which was used in designing the transistor. If it's a silicon based transistor, right, then the VBE is equal to what? 0.7, right? So the VBE is equal to 0.7. 0.7. So most of the times you will see VBE being 0.7, or if they don't give you VBE and they say that this transistor is a silicon based transistor, then the VBE is equal to what? 0.7. Okay, so before we even proceed, let's talk about the alpha gain and the beta gain. What I described just recently, that the beta DC and the alpha DC. This is the static current gain, right, between the base and the collector. Are you okay? Yes. So what is the formula for the beta current gain or the beta DC? Right. It's just the ratio of the collector towards to the base current. So that's the basic formula for it. So you should take note of it. So the beta DC or the static current gain between the base and the collector, right, is basically the ratio of the collector current over what? Over the base current. And the alpha DC, right, is the ratio between what? The collector current and the emitter current. Please take note of it. It's very, very important. So sometimes they can give you alpha DC, and out of it you need to find the emitter current and the collector current. So that, in summarizing everything that I've done here, right, we will say that the IE is equal to what? IB plus what? IC. So you need to know this formula. And what about IB? Right, IB is giving us VBB minus VBE all divided by what? By RB. You need to know this formula as well. Then you also need to know that IC is giving us what? IC is giving us the VCE, right? Let's visit that formula again. So VCC minus VCE. So IB is giving us VCC minus VCE, right? All divided by what? All divided by the RC. That's the collector resistance. You get it? And you also need to know the beta DC. That is the current gain for the beta DC, right? Is the ratio of what? Of the collector towards the ratio of the base, right? So 3 and 4, right? Then alpha DC, which is another current gain for the transistor, right? So alpha DC is equal to what? The collector current all over what? The emitter current. We should take note of this formulas very well if you are solving questions under what? Under transistors. All these ones are very, very important. As equation 1, equation 2, equation 3, equation 4. Okay, so I'm going to solve questions for now. I'm going to solve some 4-5 questions. Then we will move deep into what? Into the last session, which is the collector current curve. So let me solve one question here. The question says that we should what? We should determine the DC current or the DC gain, right? That is beta DC, and the emitter current. Emitter current, IE, 4 a transistor where IB, right? IB equals to what? 50 microamps, and IC equals to what? 3.65 milliamp. So this is a typical question, right? So let's collect our data. They say that we should determine the beta DC, right, and the emitter current. So you are looking for beta DC first. We don't know. Also the emitter current, we don't know. But we have been given IB to be what? To be 50 microamps. And IC has been given us what? 3.65 milliamps. Right? So how can we find the beta DC? We know that beta DC is equal to what? IC over what? IB. Right? And that will give us the IC is 3.65 times 10 exponent minus 3. That is the milli. All divided by what? 50 times 10 exponent minus 6. And after summarizing everything, I'm going to get 73. It's a gain. So it has no units. The current is here and the current is here. The current will cancel out. So it has no units. Right? And he said we should also find the emitter current. We know that the emitter current is giving us what? The base current plus the collector current. And that will be equal to what? 50 times 10 exponent minus 6 plus 3.65 times 10 exponent what? Times 10 exponent minus 3. At this point, you use your calculator, right? And after computing everything, you're going to get 3.70 milliamps, right? So that is it. That's the typical example. Okay. Let's solve one more question, then we will move on to the collector characteristic curve, right? And this question is saying that we should determine IB, IC, IE, right? V, RB, VCE, right? And VCB, right? Given that beta DC is equal to what? Is equal to 150. And we are given this circuit. Right? We have a resistor here, and aside this resistor too, how do you call it? We have a voltage supply at this end. Right? Then we have our NPN transistor, which is moving downwards. You get this. And it's connected this way. And at the end we have RB here, which is 10 kiloohms. We also have VB here again, right? That is 5 ohms. And VB, and this RB 100 ohms. Not RB, sorry, it's RC. So RC, which is 100 ohms. Then we have VCC, which is 10 volts, right? Then they are all connected to the ground, right? So this is a typical question, and we are asked to find IB, IC, IE, and then RB, VCE, VCB, right? You see, with this one, you see they've not given you any ideology, right? They've not given you whether it's a silicon or the antimony, right? They've not given you the values. So the best thing that you need to assume is that this is, let's say, a silicon based transistor. So VBE is equal to what? 0.7 volts, right? So with this one, we can find VRB, right? if you look at the loop, the formula is IB is equal to what? VBB minus VBE. That's the solution. I'm solving it. All divided by what? RB. So it's easy to find, how do you call it? IB. So VBB is 5 minus the VRB is giving us what? 0.7, all divided by what? The resistance, which is 10 times 10 exponent what? 3. Right. And this one is going to give us 4.3 times 10 exponent what? Minus 4. Are you okay? Yes. And with this, if we should compute in microamps, then we are going to move 2 zeros, 2 points on the left hand side, and we will increase this one with what? Minus 2. We are going to get 430 times 10 exponent what? Minus 6. Right. And this one ends up becoming 430 microamps. Are you okay? So that is the what? That is the IB. What about the IC? IC is easy to find because we know that the beta DC, right, is equal to what? The IC on what? On IB. In that case, if I should make IC the subject, I'll get IC is equal to what? IB multiplied by what? The beta DC. We're going to get 430 times 10 exponent what? Minus 6 times the beta DC, which is 150, right? So times 150. And what do we get? That is 430 times 10 exponent what? Minus 6. All times what? Times 150. If I should compute with the calculator, I'm going to get 0. Right? 0.0645. Right? And this one, if I should move 3 decimal places, I should move 3 times. It's going to be 1, 2, 3. So 64.5 times 10 exponent minus 3 amps. 10 exponent minus 3 amps. Right? And this one will end up becoming 64.5 milliamps. Right? So that's the value for what? That's the value for the collector current. So now we've been able to find the collector current, the base current. What about the emitter current? We are going to use the Ohm's, the Kirchhoff current law. That is IE is equal to what? IB plus IC. And with that one, what do we get? So IE is basically going to be what? 430. We are going to get 430 times 10 exponent what? Exponent minus 6 plus, put this in the brackets. Then we have 64.5 times 10 exponent what? Minus 3. Then at this point, you just compute with your calculator. That is 430 times 10 exponent what? Minus 6. Bracket close plus open bracket. 64.5 times 10 exponent what? Minus 3. Right. And the final answer will definitely be 0.6. This one is going to be 0.06493 amps. So if I should move 3 times 1, 2, 3, I'm going to get 64.93 milliamp. Right. That is 10. This one is the same as 10 exponents minus 3. We get it. So this is the same as 64.93 times 10 exponent minus 3 amps. That one will end up becoming 64.93 milliamp. Now we've been able to find the IB, IC, IE. Is that with the VRB? This side, the voltage drop here, VRB. And that one from Ohm's law, right? We can say that VRB is equal to what? IB multiplied by what? RB. We get it from Ohm's law. We know that the IB is what? 430 times 10 exponents minus 6. That is 430 times 10 exponents minus 6. And the RB is given as what? 10K. Right. So times 10 times 10 exponents what? Times 10 exponents 3. Times 10 times 10 exponents 3. So at the end you are going to get 430 times 10 exponent minus 6 times 10 exponent what? Minus times 10 exponent 4. Right. And this one will cancel out. It left with 430 times 10 exponent what? Minus 2. You get it? So 430 times 10 exponent minus 2, how do you call it? Amps. So if I want to make it milliamps, how do I get? I need to move backwards again. This is going to give us 4300, right? Times 10 exponent what? Minus 3 amps. Are you? Yes. And that one will end up becoming 4300 milliamps. Yes. So that is it. Are you okay? That is it. Because this one, if I should break it out again, 43 times 10 exponent minus 6 times 10 exponent 5. So 43 times 10 exponents. How do you call it? Minus 1. That one end up becoming the same thing. Yeah, I was just verifying my answer. Okay, so that is it. Then the next one is more like VCB. We are VCE, right? We apply the Ohm's law, the KVL equation that we found. That is, how do you call it? It is clear that we can say that IB, right, IC, right, is equal to what? VCC minus VCE all on what? On RC. Okay. So at this point, I'll send IC to that side. So IC RC is equal to what? VCC minus VCE. So at this point, I can make VCE the subject. With that one, I will say that VCE is equal to what? VCC minus ICRC. This will be carried to this side, whilst this one will be sent towards this side of the equation. Right? So what will be VCE? Is VCC minus what? ICRC. Which is the same as VCC was given as what? 10 volts. Right? So, and the RC is 100. So at the end, what do we have? You are going to get 10 minus what? What was IC? IC, we found that one to be what? To be 64.5 milli. So it's going to be 64.5 times 10 exponent minus 3, all times what? 100. Right? That is, let me make it clear. Times 10 exponent what? 10 exponent minus, times 10 exponent 2, sorry. That is 100. So at the end, you are going to get 10 minus what? 64.5 times what? 10 exponent minus 1. So you move one decimal point again, which is the same as 10 minus what? 6.45. Yes. So what do I get from there? Minus 6.45 will end up becoming 3.55. That is 3.55 volts. That's the VCE. Right. Then the next one that we need to find is the VCB. That's the VCB. Right. And where is the VCB located? The VCB is located at this point. That is VCB. Right. And that is more like the difference in the two voltages. So VCB is more like the difference in the all the three voltages. I have VCB here, I have VCE BE here, right? And I have vein CE here, right? And we know that this is plus minus, right? Plus minus plus minus. But if you are focusing on the KVL, right, on this loop, right, then I will say that traveling from this side, I will consider negative first. So I can say that minus VCE, right, plus VCE, right, then minus VBE is equal to 0. Yes, that is KVL on the loop here. KVL on this loop. So minus the VCB has minus as a starting point. I'm starting from this point and I'm traveling around. So the first sign I saw is minus. So minus VCB. Then I saw plus VCB. Right? Then minus VBE is equal to 0. But I'm looking for VCB. So I just send VCB to the other side. So VCB, or better still, let me say that VCE minus VBE, right, is equal to what? VCB. Okay. So that's the formula for VCB. So it's just VCE minus VBE. So we just write it and we continue. So I'll say that VCB is equal to what? VCE minus VCB, right? Or VBE. Okay. And that one gives 3.55 minus what? Minus 0.7, right? And that is 3.55 minus 0.7, which gives the 0, which gives us 2.85 volt as the final answer. Yeah, that's it. So that is the general overview for the calculations. Just go through them and you are going to be fine. So let me give a brief overview of the, how do you call it, the collector characteristic curve. I think that will be the last thing I'm going to do. The collector characteristic curve. Okay. So characteristic curve. Sorry. Characteristic curve. So assuming I have the circuit, right? Assuming I have the circuit here, it's always plotting more like IC against what? Main CE. I'm plotting IC against main CE. I have IC here, and I'm plotting it against VCE. So with the experiments, we have a connection like this. Let me have the resistor here, and I have my VCC at this point. Right. This more like an NPN transistor. So it's moving downwards. Right. And they are all connected to this end. Right. And I have a resistor here. I have a VB here. I don't know whether you've done this at the lab. Right. But you should do this at the lab. Definitely when you go for the lab class. So you'll be varying the voltages at both ends. That is VCC. You'll be varying the VCC and VBB. Right. Then you are going to know the influence of what? Of the IB. Right. Assuming I have the VCE and what? And the collector current, that is IC. So what is going to happen to the IB when, let's say, I vary the voltages? Do you get it? And it's in line with what? The collector current and the VCE. Right? So definitely the curve is going to be something like this. It moves upwards. Then it goes here. And it comes to this side. Right? I'm going to explain the curve very well. This one is done at the lab. So you are going to do it at the lab. Right? So you shouldn't panic when you go to the lab. The lab technicians are going to expose you to it. But the curve is going to be something like this. That's the IB. it will start from 0, right? Let me use a different. So it starts from 0, it moves up a little, right? Till it gets towards like a breakdown voltage, which is 0.7. That's breaking of the potential barrier. Right? Then it moves steady at a steady state till VCE gets to the maximum point. That is VCE maximum. Right? Then at that point, it goes upward. Right? So this region is termed as the active region. Active region. Right? And this region is termed as the breakdown region. Breakdown, right? Breakdown region. And this region is termed as the saturation region. From here to here, it's termed as the saturation region. Okay. So what happens at the saturation region? What happens at the active region? And what happens at the breakdown region? I'm going to explain. Right? So at the breakdown, at the saturation region, that is region 1. Right? At this region 1, you get it. The current will not conduct. Why? Because you see, this one is assumed to be at that region, both the base emitter junction and the base collector junction are seen to be forward bias. So at this region, right, they are all considered to be forward bias. Forward bias. So for the first stage, here is forward bias, and this side too is what? Forward bias. Once all of them are forward bias, it will not conduct. You get it? One should be forward bias. When we started our previous video, we were making it clear that if you have a transistor, right, the first stage should be what? Forward. This stage should be forward bias, and this side should be reverse bias. So if you've forgotten, just reverse the video and you get to see it clearly. That this side should be reverse bias, forward bias, and this side should be reverse bias. But at this region, right, the base collector junction is forward bias, and the base emitter junction is also forward bias. So it will not conduct, right, until the potential barrier is broken, right? Once the potential barrier is broken, then the base collector junction now acts like a reverse bias, right? So once it's broken, that's the second stage. That is stage 2, right? So with the first stage, this side is also what? Forward bias. So let me write it here. Stage 1. That is the saturation region. Right? Saturation region. Right? So the base collector junction is what? Is forward bias. And the base emitter junction is also what? Forward bias. So in that case, it's not active. But for the second stage, that is the 2. The second stage. Right. Let me select it. Oh, okay, for the second stage, right. This is reverse bias, while this also remains forward bias. Right. So stage 2, that is the active region. Right. The BC becomes reverse bias, and the BE remains forward bias. So in that case, it conducts and current flows with steady states. Okay. So the VBE, right, as the voltage increases, or more like as we increase the voltage, you get it? The VBE, the BC, it breaks down when the voltage exceeds it. That is found on the data sheet. So once it increases, then the reverse bias there, it breaks down. It does not act like a reverse bias again, but it breaks down. That's the stage 3. Stage 3, right? The BC, there's always a breakdown. It exceeds the set voltage hierarchy. So once it breaks down, it cannot act like a reverse bias again. And at the end, this side is forward bias. At the end, it damages hierarchy. So that's how the characteristic curve is. And the value obtained is more like the IB. The curve obtained is called the IB currents hierarchy. So if we relate the IC to the VCE, we get a curve which is the same as IB current. And we can get a series of them. That's the reason why in your handout you are having more like IB current, different IB currents at different stages. So read your handout and you get better understanding of what I'm talking about. Okay, so we are going to end the video here, and I believe it's a very long video. We are going to end it here, right? And please subscribe to my channel. It's a form of saying what? Thank you. Right. In our next video, definitely we are going to talk about the op-amp or feedback system, any of them. Anything that comes in mind, I'll talk about it in the next video. So try to watch the video, get a clear understanding, and be good with transistors. Right? Read the book that I sent to you, and also, how do you call it? Your handouts. But I'll give you a page to read to get a better understanding on transistors. And once you watch this video and get a better understanding, you read the book. And at the end, any question that comes under transistors, you'll be able to solve. At this juncture, I believe that the question that people have posted in the group on transistors, you can solve it. Okay. I wish you the best of luck and see you another time. All the best. Bye.